Good evening, everyone. We will start our lesson on spatial filtering. When we met in person, we covered most of the initial parts where we looked at convolution, how this so-called kernel moves along the image, one pixel at a time, and multiplies the underlying numbers and generates the sum as the output at each pixel. For example, if the kernel is located here, you can see these two underlying numbers, 180 and 180, are multiplied by the corresponding numbers in the kernel or the window, and the result is 140 here. So this is what 2D convolution does for a grayscale image. So what we want to do today is to understand these different kinds of kernel. So the first kernel that we considered was this averaging kernel. You multiply the underlying pixels with 1/9. If it is a 3x3 averaging kernel, you know that it must be 1/9. If it is 5x5 kernel, in order to average, you have to have 1/25 as the value in the kernel. I hope that these things are clear to you. So as before, you can ask a question at any time. You can turn on the mic and ask, or you can type in the chat so that we can understand whatever the points that are not clear. So by changing the numbers in these kernels, you can achieve a multitude of effects. This is a very important operation in image processing. For example, if you want to detect edges, actually horizontal edges that are like that, for example, in this area, if it is dark, in this area, if it is bright, this kernel can be used, so-called Sobel vertical kernel. As we mentioned last time, the kernels look for areas in the image that look like the kernel itself. So for example, if you take this location of the image, you can see there is this dark to bright transition there. So here you can see that area has been emphasized in the Sobel vertical output. If you take the Sobel horizontal output, you can see it is looking for dark to bright transitions vertically rightward, yeah. And therefore, if you have something like that, for example, here, you can see these are emphasized. So if the transition is bright to dark, they become even darker, but the value is negative but high. So because we have to represent positive and negative values in this spatial filtering outputs, we have to do this operation using floats. You cannot do it using uint8s. So uint8s, unsigned integers of 8 bits are unsigned. So you cannot represent negative values with those uint8 representations. Okay, running this on the computer is quite easy. And last time we saw that the only important operations in this are these two lines where you can see the 109 kernel has been defined here. So when you say NP1 3x3, you get a kernel of all ones generated, a kernel of 3x3, we call it a kernel. All ones, 1, 1, 1, 1, 1, 1 gets generated. And that kernel, of course, it is a floating float 32, we divide by 9. So therefore, you get the 109. So we are constructing the kernel here. Once the kernel has been constructed, which is named as kernel, we use this CV filter 2D operation to run this kernel on the image. So this is the image, this is the kernel, this is the resulting data type that we want to achieve. If you put -1 there, the resulting data type will be the type of this image. I have opened this image like this, but I think you have to open it as a floating point image. But we can run, you can run this and see. So once again, the displaying of the original image and the filter is quite easy. Also, if you want to run the Sobel filters, so you can see Sobel X and Sobel Y have been defined. Now, if you look at this kernel, you can see the first row is -1, -2, and -1, and the middle row is 0, 0, 0, And the last row, as you can see, is 1 to 1. So this is exactly what we had in the previous slide. This kernel detects horizontal edges. This is the kernel. And this is the kernel in the y direction. So remember, our convention is this y direction and this is x direction. Please remember that. So using the same filter 2D command, we are able to get this filter running and get the corresponding outputs. So you're most welcome to run these things and see. So if we briefly talk about the convolution and the spatial filtering that we do here, that means convolution and correlation. I will briefly talk about it because perhaps you have heard about the convolution in your signals and systems or DSP classes. There is a relationship that is slightly different. That's why I want to talk about it. So spatial filtering is in fact convolution. It is convolution. As the filters are typically symmetric, that means 180 rotation results in the same kernel, correlation is equivalent to convolution in this operation. Now, correlation is also the scalar product between the kernel and the underlying image patch. Therefore, it is the measure of similarity between the kernel and the underlying image patch. And we talked about that last time. That means kernels look for things that are similar to it. Because it is like the dot product, the vectors must be similar to give high output. As a result, when the kernels and patches are similar, the output is high. In view of this, spatial filtering seeks for patches in the image that are similar to the kernel. Implementing filtering using loops, 4 nested loops, is in a non-C fashion, without using C language. It is inefficient. We must not use that in Python, but although it is possible.
Sir, I have a question.
Yes.
Can we reverse the image? I mean, now we got from the input to the output, and we got this special image. Can we reverse the image from the output to the input using any special algorithm?
It's a very good question.
You can answer it later, sir, if you want to. I mean,
So I can
hypothetical.
answer that's a very, very important question. So actually now think about this. Now you have a set of numbers, okay? You have set of numbers like 1, 2, 3, okay, 4, 5, 6, 7, 8, 9. And assume that this is the image, okay? And on this we do the average operation. So multiplying by 109 and summing is the average operation. So that means we will add all these numbers and we divide by 9. So we will have 5 as the output. If you run the averaging operation with this, that means convolve with the 3 by 3 kernel with 1/9s, you will get the answer as 5. From this 5, can you recover these numbers? It is absolutely not possible, right? Absolutely not possible. So what this means is convolution, when you do it like this, it loses information. But there are algorithms that people try to run called deconvolution. So there are two forms, blind deconvolution and regular deconvolution. They try to recover the image after the blurring effect happens. So this has been a research area, but now with the deep learning, it has been comprehensively solved, I think, very comprehensively solved. Yeah, that's a very important question.
Thank you,
It is
sir.
actually especially important. For example, if you see CCTV images and those CCTV images have license plates of a car, and that is blurred. It is actually a convolution has happened. That's why the license plate has been blurred due to the motion. So can you recover that? It is very hard, but there are algorithms that people try to use to recover these things. It's an extremely important question. Thank you for that question. Actually, I got that question for the first time. These kind of classes. Okay. The convolution sum uh, uh, you must have learned in the signals and systems is this one yn discrete time convolution xn convolved with hn is xk hn minus k, and you run the summation variable like this. That's the case. So if you go for 2D, then there are two variables m and n. If you don't understand it, this is okay, because this is not a convolution class. So you have mn. So those running variables are s and k. So you can see that and t. So just take here. So you can see this is how the 2D convolution happens. So correlation, in the correlation, you had only noticed the difference. In the correlation, you can see that this negative sign is not there. Negative sign is not there. So what that means is the image or the kernel is not flipped in the correlation. In the convolution, it is flipped. So I'll show that with an example what happened. So consider that there is an image like this. This is an image. It's a grayscale image, and there is only one here. And this is the kernel 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the kernel. So we want to apply correlation, and convolution and see what happens. Before applying, let's pad the image. So this is the original image. I have padded it with zeros all around it. Otherwise, I cannot locate the center of the kernel at the very corner. So now my thing is, I locate the center of the kernel right here and multiply the underlying numbers and get a value. So the center of the kernel, when you locate there, the kernel overlaps with these pixels, right? So you multiply all of them with zeros, like 1, 2, 3, all of them. So therefore, the value that you get there is 0. 0 is the answer. So you move that by 1 pixel to the right, the center, again 0, 0, 0, 0, zeros you get. But when the kernel goes to the next row, that means when the kernel center is right here, this 9 overlaps with this 1 9. So therefore, you get at that location, you place 9 there. At the center of the kernel, you place that number, right? 9. Then you move here. Then you know that the 8 will overlap with this 1, and then you get 8 here. Then you move the center here, and the 7 will overlap with this 1, and then you get 7 there. So on. And then you can see in the output that you got this filter flipped by 180 degrees. It's flipped. That's not correct. But if you first flip the kernel, and then run the operation, you can see that the filter gets located at the center. This is the expected operation. So that's why in the convolution we do this flipping, reversing of the convolving variables.
So what's the difference in symbol between the star with the circle around it and the star without the circle around it?
Yes, exactly. That's the difference between the correlation and the convolution. For the convolution, the standard symbol is the star. Star with the circle is the correlation, where the kernel is not flipped. You see, when this negative sign is not there, it's not flipped. But you can see the flipping is required, right? If you don't flip, you get a weird thing here. So that's why people do. But if the kernels are symmetric, like for example, in our kernels, we had all 109s. So even if you flip it, you get the same thing. So therefore nothing bad happens when you have symmetric kernels. Okay. So the properties of convolution that you may have studied in your signals and systems apply. That means if you filter two images, it is equivalent to filtering them separately and adding. And you can, shifting operation is possible. Commutative, it is like 4 times 5 is equal to 5 times 4, right? That is called the commutative property. So this property is applicable to the convolution also. So therefore, it does not matter what you consider the kernel, what you consider the image, it can flip. And then associativity, that means you have two filtering kernels. Consider that A and B are filtering kernels, C the image. So you can first apply B onto the image, and then into the result you apply the A. Or you run this convolution between the two convolution kernels and then apply on the image. Both these things are possible, but the second operation is usually very much computationally less expensive. So therefore, there are computational advantages if you use some of these operations. Okay. So at these edges, we considered that there is a problem where the kernel does not fully overlap. So in OpenCV and so on, there are different kinds of ways that border replicate. Now, if you consider this as a one-dimensional image, you see these are the extreme pixels, right? So you can repeat the same pixel line. That is possible so that the kernel gets fully overlapped with the image and so on. So otherwise, I will not describe them. If you need, you can look at them and study what those things are. Okay. So now let's do some kind of a fun exercise of so-called sharpening. This is called image sharpening. Now, what happens there is, this is an example of the use of this filtering. As an example, I'm doing. So you have an original image here, and you smoothing it out by Gaussian filtering with the Gaussian kernel. You smooth it. When you smooth it, if I ask you whether you what kind of frequencies do you lose when you smooth? When you smooth,
Low
what
frequencies?
when you smooth, you lose high frequencies. Low frequencies are retained. You
Oh,
can see sharp transitions are gone, right? Sharp transitions are gone. So high frequencies are gone. So this is a low pass filtered version. It's a low pass filtered version. Okay. But when you take the original image and subtract the low pass version, you get the high pass version of the image. High pass filter. That means this is high frequencies. This has high frequency. You can see high frequency means the edges are present here, right? Here the edges are blurred. Okay, so I think you can understand the first row. In the second row, what you do is you take the original image, take this one, add a certain portion of that to it. You can add a weighting factor also, lambda or something. Certain portion of that to that original minus smooth one. So then you can clearly see that the original image gets sharpened, right? So the teeth are sharpened. This is called sharpening or unsharp masking. So let's do that. And then we'll be able to see that edges get sharpened. Okay. So let's go back to our Visual Studio Code. Locate the images. Yes, I will sit down with that.
so I have a question. Is there any limit to the size of the image you can load and run these kind of algorithms?
There is a limit, but that limit is quite large because we have large memories now, right, on computers. Memories
Okay.
are quite large, so limited by the amount of memory the compute has, but that amount of memory is quite high, so it does not matter.
Okay.
So if that becomes a problem, then there are ways to, load parts of the image. So I do not know those though.
If I put it another way, is there an optimum picture size we can work with when we are dealing with images?
Not really, not really. Yeah, any size is generally okay.
Okay, sir.
Okay. So I hope you can see the screen. I will slightly enlarge also. Okay, what we want to do is the sharpening operation. So import CV2 as CV, and we can import matplotlib.pyplot as PLT. This is what we want. Um, mm, the original image, we can call that original image as F or something. Let's call it F. F equals cv dot imread. Actually, this is in the images folder, and I want to open the image of Mr. Tom Cruise, Tom, and we have to open that as a grayscale image. Cv dot imread grayscale, and I want to open that as type float32 as a floating point image. I open. I need to import numpy also. Now image has been opened, but remember always we have to assert if f is not none. Otherwise, we cannot find what has happened to our operations. It's very difficult to diagnose that. Okay, so let me run this. Yeah, it ran without a problem. Okay, now let's blur the image. So kernel size, let's say kernel size is 9, and then let's generate a kernel, Gaussian blur the image, F smooth. Okay, so it's giving me how to do that. Okay, Gaussian blur, CV dot Gaussian blur. The kernel size, Gaussian kernel size is K, kernel size by kernel size 9 by 9. And then this, I don't know what that is. But the parameter is that's okay. This will work. So we have the smooth version there. That's fine. Then how do you get the high pass version? F high pass version. High pass version is originally F minus F smooth. Now we have the high pass version. Then what we need to do is to get the sharpened version. If sharpened version, you can just add them. But I like to do CV weighted addition properly. CV dot add weighted if and 1.5 times the smooth version, and I add 1.5 times smooth version. Okay. Smooth version, I'll add about 1.5 times of that, and about just 1 of F. So this is the multiplier for the F. This is the multiplier for the smooth version. Okay, now I have them. So I have to now create a figure and display them. So I have the code written for that part. I will just cut and paste that. I do not want to write that. So you can see I have created access, number of rows, number of columns, 2. Figure size is like that. So first of all, I show the F original image, and then in axis 0, 1, I show the uh, smooth image. In axis uh, axis okay, we have to first normalize it to be able to display F high pass, and then I show F high pass version, and then I show F sharpened version. This is the code, very simple code. Okay, let's run this and see. It's very quick, right? You can see. You can see the original version and the smooth version. You can see it's blurred out, and the high pass version and sharpened version. This has brightened up because we added this by 1.5. Trying to see what is the mistake that I'm making there. I think let's add just 1.5, maybe too much. Oh, I'm adding the smooth version. This is very wrong. I want to add the HP version. That's a mistake. I added the wrong one. Okay. Yeah, now you can see it's clearly high and really sharpened. So teeth, for example, are very much sharpened. So it's a very simple operation that we ran. As you can see, you from the original we subtracted smooth one, and then you got the high pass version, and that high pass version we took and we added with the original to get the sharpened image. Okay. So now we are happy about these operations. You can see multitude of things can be done with this. But about the Gaussian smoothing, we want to study further. Gaussian smoothing. Any questions before I move on? Okay then. I hope all of you are happy about it. Maybe you can do it on your own. The sharpening, it's very easy. Okay. Um, Now, when you filter using the averaging kernel, so I have shown the averaging kernel like this. What that means is if you have a, for example, 5 by 5 averaging kernel, you remember it's a 5 by 5 window, like so, and all the numbers are 1 over 5s, right? 1 over 25s. 1 over 25s, I'll write only one number there, right? And if you take the area around it, it's nothing, right? It's black. Area around is black. So that's why we are representing that as black here. And these 1 over 5s we are representing as bright. So this is the kind of averaging kernel. We call it a box filter because it looks like a box. So if you run this box filter on an image like that, this boxy nature will come. There's some boxness in the output. This is not good. So therefore, we want to, rather than box filtering, we want to filter with a Gaussian kernel. So when you Gaussian smooth it, it's a nicely smoothing out. So that's why we want to further study about this Gaussian filtering, because Gaussian filter is a very important filter for noise filtering. So now we want to generate the Gaussian kernel by ourselves and generate these images. So you can see this is the Gaussian. So you know what the Gaussian is, right? At 0, it will have the highest value, and then it tapers off. This is in 1D, right? This is in 1D. This is the kernel in 2D. 2D with mean 0. So e to the power 1 over 2 pi sigma squared e to the power minus x squared plus y squared divided by 2 sigma squared. This is the Gaussian kernel in 2D. Before we go to the computer, let's do a computation by hand. Let's do a computation by hand. That is, the question is, construct a 3 times 3, 3 by 3 normalized Gaussian kernel. Okay, 3 by 3 normalized Gaussian kernel. So if you want to do that, I look at the equation. This is the equation. That's the equation. So let's do this. Here is my 3 by 3 window. That's a kernel. Now let's look at the indices of this kernel. Okay, this one, this is the vertical, this is the x direction. And this is the y direction. And this index is 0, remember that. The center is 0. This is minus 1. This is 1. This is 0. This index is minus 1. This is 1. So therefore, I'll write the coordinates here. The coordinates of this cell So coordinates of this cell is 0 and 0. 0, 0. That's the coordinate of that cell. So because we have to normalize this, because we are normalizing, I can actually ignore this normalizing constant. This one I can ignore. And I can just compute e to the power of minus x squared plus y squared divided by 2 sigma squared. Oh, did not tell you what sigma is, right? So let me do that. Kernel with the sigma equals 1. It's okay. That's 1. I destroyed everything. That's okay. Sigma equals 1. So indices again, 0 here, minus 1 here, 1 here, minus 1, 0, 1. Because we are normalizing anyways, the function that we have to consider is only e to the power of minus x squared plus y squared divided by sigma is 1, 2. As sigma is 1, just put 2 there. So this is what we need to consider. So first consider the case right here. Right here, the indices are 0 and 0. I wrote them in small numbers there. So you apply 0 for the 0, 0 location. Let's do the computation first. So e to the power x is 0, y is 0, divided by 2. That's equal to e to the power 0, 1. So you can see get 1 here. I hope that's clear. Is there a question about that or is that clear? Okay.
It's clear.
Then, yeah, thank you. Thank you very much. Then let's take, for example, this location. This location, x coordinate is minus 1 and y coordinate is 0. Y coordinate is 0. So let's consider that one, minus 1 and 0. With that, you will have e to the power minus, anyways, x squared, so minus 1 squared plus 0 squared divided by 2, and that is e to the power 0.5 e to the power minus 0.5. That is, I have a calculator, I can compute that.
1.64.
Minus point e to the power minus 0.5, 0.6065. That's what I get.
Ah, sorry, sir.
Did you put the minus sign?
No, sir.
Yeah, please, minus sign is required. 6065. I hope that's okay. So this one is 0.6065. 6065. So see, now let's take this location, for example. This location. Here, my x coordinate is 0, y coordinate is minus 1. But you will see, because these are symmetric in x and y, you get the same number there. So I can write it if you like. So for 0, minus 1, you get e to the power of minus 0 squared plus minus 1 squared divided by 2. Again, you get e to the power minus 5. So you get the same number. So you can see this is 0.6065. This will also get that. This will also get that. Okay. It's very easy. So I will write that also in the same color. Then we have one more location, 4 more locations. If you take this one,
0.1353.
1353. So yeah, most probably. So we will check that. So minus 1, we have minus 1 and minus 1. So you will have e to the power minus 1 squared plus minus 1 squared divided by 2. That means you will have e to the power of minus 1. E to the power of minus 1.
0.3678.
0.3678. Thank you. That's correct. 0.3679, right? 9. Again, I round it up. Round it up. 0.3679. So I think you can now notice that all these numbers are the same. 3679. 0.3679. 0.3679. Thank you very much for attending to this. But now this is not still normalized. This is the unnormalized version. So to normalize that, we have to divide by the, let's call it G. We have to call it by the sum of that. So we have to get G divided by the sum of G. Let me write the sum symbol. By the summation of G. Right. So let me do that for this one. 0.3679 times 4 plus 0.6065 times 4 plus 1. That's the sum. Sum is 4.8976, and on top of that you have this kernel, 3 by 3 kernel. This one. So therefore, finally the numbers that you get are, each of these you have to divide by 4.8976. So 1 divided by 4.8976 is 0.2042. Then 0.6065 divided by 4.8976, 1238. I hope these numbers are correct. 0.3679 divided by 4.8976, 0.751. Zero point zero seven five one. 0.0751. Okay, you have to write this. I will not write this. So you can see this is the normalized Gaussian kernel computation. So I hope you are happy. Anyone who has a question about this? This is fine on paper. So see, on paper you do. Now we will do it in Python.
So when the matrix is larger, is it the same approach we are going to follow?
Yeah, it is the same approach. For compared to the Gaussian kernel, this is the approach. But of course, yeah, there is a way of doing it faster. So I will show that. Yes, yes. There is a way of doing that faster.
Hello, sir.
Yes.
When we write this value, are we not adding the 1/25 term?
That's an important question. We don't have to because we are anyway normalizing now. So this part, that's a valid question. This part we can ignore because anyway we are normalizing by the sum of the kernel, right? So therefore, it is okay because even if we multiply this by this number, all of them, you are dividing it by again. So therefore, it's okay. That's the reason.
And thank you, sir.
Okay, now let's do this in VS Code. VS Code we will do instruction. So import numpy as np2, np not np2, np. Okay, so first of all, we need the half size of the kernel. So half size. Half size, let's call it half size is 1. Okay, if you take 3 divided by 2 is 1, so half size is 1. Okay, that's a half size. And then we need the sigma equals 1 in our case. If we turn off this is annoying actually. Yeah, sigma is there. So then we need to generate the grid. So for that, I will have to generate an x equals np arrange half size to half size, half size to half size plus 1. Okay, if I print x, you will see, so you get -1, 0, 1. Okay, those are the coordinates I'm generating. So I'm generating y also the same way. So if I print y, you will get minus 1, 0, 1. That's okay. Now I have to get yx equals this NP mesh grid. So we are constructing the so-called mesh grid. So if I construct the mesh grid and show y, you will see y. So in that mesh grid, you can see this coordinate is minus 1, 0, and 1. Those are the y coordinates, right? If I print x, okay, let me print both of them together. Print y, comma, okay, x, comma, y. So you can see print a new line character, okay. So you can see this is my x coordinates, these are my y coordinates. You can see x coordinates minus 1, 0, 1, minus 1, 0, 1. They are always the same, right? Y coordinates minus 1, 0, 1, minus 1, 0, 1, minus 1, so horizontally rightward. So I have my x and y coordinates. Now I can directly compute the Gaussian kernel. So G equals NP e to the power xp, exp. What is our formula? X squared plus y squared divided by 2 sigma squared. This is our formula. Can you see that? X squared plus y squared divided by 2 sigma squared. So I directly calculate G. That's okay. Then I need to divide G by sum of G, right? Divide D by the sum of G. So divide D equals means the G is divided by the sum. So I can otherwise write it like that. G divided by the sum of G. That's okay. Now I have the G. Then I can print G. This I don't need. Oh. So you can see the values that you got, we have obtained, right? Exactly the value, no, exactly, sir. Approximately the values that you got. I hope that you're happy. What you manually got is what this is. But this is not what I want. I want to get a 3D picture of this. For that I will have to do something. I need to put this code I have. Okay, here is the way to do that. I'm going to plot 3D picture. 3D picture of that. So for that, I have to say subplot 111 projection 3D. And I have to say plot surface. You have to give x, you have to give y, and you have to give the g that you computed. But that you cannot see with this kind of half size of 1. You have to give a large 1. So let me give large 1 like half width of 50 or something. So 100 by 101 by 101 kernel. So I will not print it because it will be a very large one if you print it. It is too large. So we will increase the sigma maybe to up to 10 or so. So it spreads out. So now you can see, right? It is beautiful, right? It is very beautiful. That's the Gaussian kernel in 3D. So you can see that sigma, if it is too small, you cannot see it. So if you want to have sigma is 1, I think the size of the kernel, it has to be, I mean, sort of small. Otherwise, you cannot see that it's too much of a peak. They are also like it's too much of a peak. 15 and 3 or something. Now you can see it's okay. But I like the previous one, 50 and 20 or so. Nice. Quite nice. 20 is too large. This is only for visualization. This is nothing more than that. I'll give you a little bit of time to do it by yourself and be happy about it that this is working. Very small number of lines, right? With that you can get it. That's the thing about Python. It's quite easy to code because only a few lines are required. Any questions or concerns?
So when we are creating this, we call it
Yes.
matrices, in which instances do we need to make copies of them before we do the coding further down?
That means if you want to go to another cell somewhere down. Is that what you
Like,
mean?
so for example, like we create some kind of matrix, but we want to keep the original, state as it is, and then create a new one, a copy of that, and then start modifying that.
Yeah, if you want to modify it and keep the original one, you have to make a copy of that.
So, like, in what use cases would that be useful in this kind of scenario?
Yeah, if you want to keep the original for some reason, I do not see now. For example, if image is also matrix, right? If you want to keep the original image, then you can keep a copy of that. You can create a copy of that and do the modification on that.
Okay.
Yes. Yeah. Especially applies to an image. So this Gaussian kernel we constructed, and you can apply that to the filter 2D functions if you are writing them. The kernel that you constructed, it is possible that will work. But I will not do it right now. I think you know how to, but maybe I will do it. Okay, I will do that. So I will copy the whole thing here and show you how to apply that. So let's make the half kernel size 1, maybe 2. That means a 5 by 5 kernel. And then sigma, of course, is 1. And then I have the Gaussian kernel. So let's see, if you like, you can print it. That's our 5 by 5 kernel, you can see. So I want to apply that to an image. So let's open an image and apply that to that. So to open the image, I can use the same code. So therefore, I will copy it from here. Okay. Image Tom's image. So that hide of Tom's image now. I want to get the image. Right, the Barbie image. Okay, this is what I'm going to open. That's fine. Then kernel has been constructed. F smooth, we can apply the CV filter 2D and F1G. That's all you need to do. Then display all of them. So all these things are okay for displaying original, the smooth. Yeah, sure. That's it. So you can see This is the original image. This is not smooth here because the image is a large image. So we have to have a large kernel to smoothen that or make it slightly smaller. Let's small open in a small way. There's a way to make that small. Scale 2 or something. Let's see. Scale 2. I cannot get the prompt, so that's why this is happening. Some of these commands I don't remember myself. So let's see. That's okay. Let it be. Let it be. So I will increase the kernel size. So kernel size, let me put a maybe uh, 15 by 15 kernel with sigma equals 5 or so. So you can see clearly it's smooth. So you have to increase the kernel size and sigma based on the image size. Otherwise, you don't get the sufficient blur. So this is not using OpenCV kernel construction, but we used our own. But OpenCV had the Gaussian blur function. If you remember here we used the Gaussian blur function, but here we use this our own kernel to do that. I hope that's clear to you. Okay, let's go back to the slides.
So I have a question.
Yes.
Now I noticed that we are using JPG for our testing here. Can we use other file picture formats?
Yes, you can use almost any format. PNG.
It doesn't affect the analysis.
Yeah, it's not noticeable. It's not
Okay,
noticeable.
sir. Okay, sir. What
But
about sir
JPG,
that raw? There's a in the camera they have raw format or something. Can we
raw
use that?
format, I'm not too sure whether OpenCV can open that.
Okay, sir.
Yeah, so in JPG and so on, you actually compress. So
Because I think raw format is the highest quality, isn't it? I think
yes,
out of the
yeah. So image compression format, it's very important to know those things. So
it's called vector also, is it, sir? That raster vector.
yeah, so now these are different kinds of formats, as you can see. So if you take, for example, JPG, JPG is a compressed format. Lossy compressed format. Lossy means some information is lost. But if you take PNG, that's also a compressed format. There's no loss there. Um, then these are called raster images. Then if you take these images like raw images, apples, these ones, raw images, I don't think they compress. There is no compression there. You can do arithmetic compression, but lossy compression is not done. So that's why photographers, I think they want to work with the raw images.
Yes, sir.
I think that's what you meant. So this BMP is also compressed but lossless compression. So talk about maybe you have to read an image compression article. So there's no time to read all of them now. So how the compression happens and so on. JPG compression, what is lossy compression, what is lossless compression, all these are there. So okay, for those kind of things, I think ChatGPT output will be very useful. So you can say, briefly teach me image compression formats, image compressions, and file formats. So these things using ChatGPT is very good. So this is there are two things, lossless and lossy. And file format is called the compress container, and there's a compression algorithm also. So lossless, no information is discarded. Perfect reconstruction is possible. Typically, compression receives 1.5 times or 3 times. So common techniques are so-called run length encoding, because these are called arithmetic encoding. No image is lost. So they are used for medical imaging, scientific images, and so on. Lossy, you can compress by 10 to 50 times. So they are using the discrete cosine transforms of wavelets. So JPG uses discrete cosine transforms. Wavelets are used by JPG 2000 and so on. So perceptual redundancy removed. That means you cannot see it that information has been lost, but actually information has lost. With image photography, streaming, social media, these are the ways. So major file formats. So JPEG, if you take JPEG, it's a lossy. It's all lossy ones. So 8x8 blocks of DCT transforms are used to do that. PNG is lossless, but there is a compression. So you can see the compression is lossless compression. And then GIF lossless, but there's a compression there. And TIFF is lossless. It's important for medical images and so on usually. Then Hike, I think this is the Apple's format. It's lossy based on HEVC. It's an advanced compressor. And yeah, these kind of things. So you have to briefly. So what about raw format?
So does that mean, let's say we are doing some kind of processing and we initially have the raw format and the file is too large, then we can convert to a suitable format and then do the processing.
Also, but the camera itself has a chip to compress.
All right, sir.
Yeah.
To the specific format we need.
Yes. Yeah.
Okay, sir.
RAW is usually nearly lossless. So these cameras, so for example, Nikon has NEF output, Sony has like that. Those are these. They have their own format. That's a very important question. You have to know about image compression up to a certain level. So now when you are choosing the Gaussian kernel, we saw that when I had to smoothen out that Barbie girl's image, I had to increase the kernel size. And when I increased the kernel size, I had to increase the sigma also. So what is the relationship between the kernel size and the sigma? So you can see from this diagram that relationship. I have plotted the 1D Gaussians. You can see in this case, sigma equals 1 has been plotted. That sigma equals 1 is the blue curve. And sigma equals 3 has been plotted. That's the red curve. And sigma equals 5 has been plotted. That's the black curve. You can see the black curve has still not reached zero. So therefore, the full effect of the Gaussian is not there in the black curve because we have curtailed it by -10 from -10 to 10. So I think, not I think, so sigma equals 1, it has been already curtailed and we have too much kernel size for that. Sigma equals 10 may be the optimal size. So therefore the rule of thumb is set the filter half width to about 3 times sigma. That's the rule of thumb when you construct Gaussian kernels. Okay. Then this slide answers one of the questions is when you construct large kernels, is there a faster way to run this kernel? There is. So that is an important observation. Now, if you take this is like that, if you take the a to the power m plus n, right? Plus n. You know that you can write that as a to the power of m times a to the power of n. Using rules on indices, you can write it like that. So here you notice that there's an x term and a y term. So similarly, you can write it like that, the Gaussian. So what that means is this is totally dependent on x. This is totally dependent on y. What that means is running a y-dimensional kernel first and an x-dimensional 1D kernel next gives you the full effect of running a 2D Gaussian kernel. This is called separability of Gaussian filters. This saves computation power much. The 2D Gaussian can be expressed as a product of two functions, one a function of x and the other function of y, as you saw here. In this case, the two Gaussians are identical 1D Gaussians. The separability means that the 2D convolutions can be reduced to two 1D convolutions, one among rows and one among columns. What is the computational complexity of filtering n by n image with an m by n kernel? So remember, if m by n is like, for example, 5 by 5, at every location of the pixel, you have to do 5 by 5 multiplications. So therefore, the computational complexity is n times n at each location times 5 times 5. So we call it order n squared m squared. This is very high complexity. Order n squared m squared. We call it big O. That's the computational complexity. Yeah. But when you run this, you can see that m squared thing is gone. This one. So this is that. What is the complexity if the kernel is separable? It's n squared m. Okay, you can write twice n squared m, but that twice you discard because from the computational complexity theory. This is the thing. Yeah, they can be separated and you can implement them also. Okay, another concept is the thing about the Gaussian noise and the amount of noise and the size of the filtering kernel that you need. Mathematical model, some of many independent factors is noise. Good for small standard deviation assumption, independent zero mean noise. So, for example, if you take image noise and if you take a scan line, if you take a line along this image and if you try to plot it, and if you have a small amount of noise, you don't see that noise, the scan line. So each amplitude has been seen as a height. This is a bright area, it's a height. So here, when you add more noise, you can see a lot of variation in the signal. So image is there and the noise process has added the noise, and that noise is a Gaussian noise with some sigma. So this is exactly what we have done. So varying sigma, I have added noise 0.1 and 0.2 and so on. So when you add noise, you can see the noise, the graininess of the image has become grainier and grainier. To handle that noise, I had to smoothen with the kernel with increasing sigma. See, I'm smoothing with an increasing sigma. So you can see, because we have added very small amount of noise, if you smooth with 1 pixel sigma, you sort of get it removed. Here, 2 pixel. So I think you can understand that, right? So this is, if you have a lot of noise, you have to use a large kernel. 2 pixel is also not enough. So reducing Gaussian noise, smoothing with a larger standard deviation suppresses noise, but also blurs the image. Okay. That's about the Gaussian. Okay. Then now let's look at the median filter. So median filter is very different from the Gaussian filter. Now this is inability to reduce the salt and pepper noise with Gaussian filter. Salt and pepper noise is like you have an image and you sprinkle salt and pepper, white and black dots. That's salt and pepper noise. So this image has salt and pepper noise. I have added salt and pepper noise there, and I am smoothing with the Gaussian filters of kernel 3 by 3, 5 by 5 and 7 by 7, so noise is not reducing. But if I median filter with the 3 by 3 or at once, the noise gets seriously reduced. So what is this median filter? That's a question. Okay, I'll tell you how it happens. So assume that within this 3 by 3 window, these are the values of the image: 10, 15, 20, 23, 90, 27, 33, 31, 30. So you can clearly see this 90 is an outlier. So what we do is we order these sort them. So you can see it's from small to large. So largest value is 90, and pick the middle one. Middle one or the median. We call it the median, right? Pick the median. If you pick the median, these outliers, they get thrown off. The median filter operates over a window by selecting the median intensity in the window. Is median filter linear? It is not linear. Linear means you have to be able to do the filter with the matrix multiplication. But this cannot be shown with the matrix multiplication. Therefore, it is not linear. So salt and pepper noise can be removed using a median filter, but this median filter is not a linear filter. Then the final thing about this spatial filtering is bilateral filter. Okay, it takes a little bit of time to understand the bilateral filter. What is bilateral filter? It's a nonlinear, edge-preserving and noise-reducing smoothing filter. Edge-preserving. It combines domain or spatial filtering and range intensity filtering. Useful in denoising while preserving edges, unlike Gaussian smoothing. Okay, first of all, let's see the effect. So I have taken this original image and I have applied Gaussian filter. So you can see all the edges have been blurred. These edges have been blurred. But if I apply a similar bilateral filter, you can see the inside the structures are smooth, but the edges have been preserved. You can see the edges have been preserved, but inside they have been smooth. How does this happen? It happens because of these two things, domain and range filtering. So this is the domain part and this is the range part. Although this equation looks complicated, this is very easy. Now this Gaussian kernel with the sigma s spatial standard deviation considers the distance between the pixel in question, that means the center, and another pixel nearby. It is the same Gaussian filtering that we considered. Remember, to the exponent of the Gaussian, we put x and y coordinates. That's the distance from the center. Okay. But in the range filter, with sigma r as the standard deviation for the range one, you don't have x and y, but you have the pixel intensity, ixi, ix and ix. This ix is the intensity of the gray value of the image at x, at the location x. Okay, x represents two numbers, okay, x coordinate and y coordinate. Ixi is a nearby location, intensity at a nearby location. City at xi. Xi. Please get xi. So now if you take let's take two locations. Let's take two locations. Okay, I will draw large rectangles, but they are not large. Huh? 2 pixels like this, okay? They are larger than pixels. Assume that this is my x. This is my xi. Okay? These are two close by locations within the window. So the two intensities are very different, right? This will give me a large number. Let's say the intensity difference is about 50. So this will give me 50. This number is 50. Now to the Gaussian's exponent, if you put 50, that means e to the power of minus 50, e to the power of minus 50. What do you get? You get 0. If you put e to the power of minus 50, you get 0. So therefore, at that point, there is no smoothing. Smoothing does not happen because of that 0. So, but if you take an area where somewhere here, you take two close by pixels x and xi, the intensities are the same. So for that, you will almost get some number like 0. Then this Gaussian result will be 1, e to the power of minus 0, 1. Then the smoothing will happen. So you can see how the bilateral filter works. When there is a large difference between intensities of within the window, there is no smoothing. When there is a small difference between intensities within that window, that means sort of a similar color area, smoothing will happen. This is exactly what you have noticed, right? Across the edges, there is no smoothing across edges, but within sort of similar regions, smoothing will happen. That's the bilateral filter. It does edge preserving smoothing. Any questions about the bilateral filter? It's a slightly difficult filter to understand.
So can we break down that bilateral filter into two parts, like mathematically? Like sum of the first part and maybe multiplication in the sum of the second part, or
Anyway, multiplication has to happen all together.
within the
Mathematically, you
summation?
can break it, but in the computationally, it has to happen all at once.
Okay, sir. So another small question is not related to this, but I was just thinking when we are converting color images to black and white images, I saw in the AI that there's like 2 or 3 methods like this: REC 709, about RGB2, RGB, and the standard luminosity REC 601. So some different standards of converting color to black and white. Is that has any effect on this analysis?
Yes, when you have RGB, you have three colors, R, G, and B. And then from that, how do you extract the intensity is a question for people who study image color. So we just use OpenCV to do that. I don't know how OpenCV does that. So like you say, there are different algorithms
Yes.
of converting. Those are represented by 3 by 3 matrices. 3 by 3, not 3 by 3 matrices, like three numbers. How you combine R, G, and B? There is an effect. But since we are using one single software, we don't have to worry about it.
Okay, sir.
Definitely, there is an effect. Okay, so that's all we want to cover about the spatial filtering. I hope you got a good understanding about spatial filtering and you are happy. So in spatial filtering, it all depends on the kernel. It all depends on the kernel, and by constructing these kind of different kernels, you can achieve the different effects that we want. So last time I showed these kind of different kernels, the different filterings available in popular photo processing software. They are very useful to noise filter photos, add different kinds of effects, detect edges in photos, and as we showed, the sharpening operation, blurring operation, all these things can be done with this spatial filtering. But one thing is those in the spatial filtering, those kernels, as you see, are hand designed. So, for example, Sobel kernel is hand designed. Gaussian kernel is hand designed. So, but when you think about the convolutional neural networks, those kernels are automatically discovered.
So can I ask a question? In
Yes,
the
sure.
non-visible spectrum, I mean, like what the human cannot see, certain cameras can, like IR and things like that. Can we use this similar kind of filtering approaches?
You can use the question is when these are called hyperspectral images. These spectrum that the camera sees is RGB, sensitive to the human eye. There are cameras that can sense other than thermal cameras. There are cameras that sense IR. Those kind of cameras are there. And for those also, the same kind of operations can be applied. But of
Okay, sir.
course, if you want to deeply study these areas, maybe there are things that I do not know about them for sure.
Okay, sir. Thank you.
Yeah. Let's if you open the butterfly image and then filters. The filters have so many of them, right? For example, blur. So this is the Gaussian blur, and we know how to apply we actually applied Gaussian blur, right? So see, this is the Gaussian blur. You can increase that Gaussian blur. So now you know how that is applied, right? But there are many other filters. Focus blur. So the people have discovered how to apply them. So you can see here there is a focus, outside there is no focus. That's called focus blur. So they are applied spatially. You change them. So other blurring, mean curvature blur, median filtering that we studied, and many other things are there. So enhancements, anti-aliasing, increase, high pass. So if you do high pass, you can see the edges can be found. This we know because we have already done the high pass version for this Tom Cruise's sharpening work. Enhance, high pass. Okay, all these things are there. De-speckle, sharpening, unsharp masking. This is exactly the sharpening that we saw. Amount of sharpening you can increase, and then you will see that it gets sharper and sharper. I don't know whether you can see the effect. I can see the effect. Yeah, you can see the image gets sharper. Right? Example, grass gets sharper when you increase the sharpening. These are operations now. I think you can understand how they must be happening. Of course, I don't have the knowledge to explain each one of them. You have to study how they must have done some of these filters. I myself do not have that kind of knowledge. I don't know. So, okay, yeah. So that's what I wanted to show you. Okay, so there we finished the lesson on spatial filtering. If you want to pre-process images to be suitable for an industrial application, we will do some of those applications when we finish studying some of the lessons. These operations become very useful. Okay, now let's look at slightly more high level operation, detecting edges, corners, and blobs. Edges, corners, and blobs. Yeah. Okay. First of all, edge detection. So you can see here clearly what an edge is. It's a sharp transition between colors. So edges are very important because artists draw images based on edges, and we at the school also, first of all, we draw the edges of the image using a pencil, then apply the color. So identify sudden changes or discontinuities in an image. That's the purpose of edge detection. Intuitively, most semantic and shape information from an image can be encoded into edges. So human beings are very sensitive to edges. So edges can come into the picture because of a discontinuation of color, illumination discontinuity, discontinuation of color, depth discontinuity, and then surface normal discontinuity like that. So now let's look at an edge, how it looks like. So let's take this image. It's a black stripe on a white page. So here I have a scan line. This is called a scan line, one single line. Okay. Now here you can see the image is bright. So intensities are high. In this range, image is dark. Intensities are low. Here the intensities are high, bright. So if I draw a graph of how intensities change, do you agree that this is the case? Okay, this is that bright area. This is the bright region. This is the dark region. This is the bright region again. And the transition, as you can see, is slightly smooth, not an abrupt transition. So that's why this transition has happened over a small interval, right? For some kind of a small interval here. So you can understand that this intensity function across the scan line. I hope you understand that. So to detect edges, you have to see how this function transits, right? Discontinuities of this function. How do you measure that? You get the derivative, first derivative. So first derivative is what? So if you take a function like that, okay, what is the derivative? Derivative is a constant, right? It's x. For example, it is like x. Fx equals x. Derivative is 1, right? But if you take a function like this, right, x squared, derivative of the differential coefficient is x. So I think we have studied them for A levels. So this is what we're talking about. So here it is a transition from bright to dark. So it must be a sharp negative, large negative derivative must be there. Here transitioning from dark to bright in this thing. So there must be a high peak here. So if we differentiate the image and find peak values there, we find the edges. That's what we want to do. Okay. Edges correspond to extrema, that means high values or low values of the derivative. I hope that's clear to you. So how do you do that? It's very simple. Okay, so let's see how to do that. Now, what we have to do is we locate a window here. So I'm drawing this window large, but it's 2 pixels. Huh? What I want to do is, this is to detect the derivative. I take the value here, I take the value there, and I have to subtract and divide by this distance, right? And set that distance to 0. I hope you remember this. If you have a function like this, how do you find the derivative? You take a point called x. Naught is x naught, right? And you select a nearby point. This we call x naught plus x naught plus epsilon. Let's say small number. Okay. So what is the value of the function here? Value of the function here is fx naught. What is the value of the function there? F x naught plus epsilon. X naught plus epsilon. So we subtract and divide by that and set the limit to 0. That's how we find the derivative, right? So if x naught plus epsilon minus fx naught divided by that difference, you know, this difference is, you can see epsilon is the difference, epsilon, and set the limit of epsilon, we have to set it to 0. That's how we get dx by df by dx, right? We call this df by dx. Yeah. So that's exactly what we had to do. So, but when you have an image, you cannot set the limit of epsilon to 0. The most small number that you can is 1 pixel. So you just have to subtract close by ones and divide by 1. That's all you can do in discrete time. This is in continuous time, right? Okay, so now I hope that you can appreciate these formulas. So in this formula, you have increased x by a small amount, subtract the function, divided by epsilon, set the limit to 0. But remember, these are two-dimensional functions, so y stays constant. Y is y. Because y stays constant, we call it partial derivative. That is the partial derivative with respect to x. So, but because we cannot set epsilon to very small, you set it to 1 in images. You cannot set to something lower than that. Partial derivatives. So for discrete data, we can approximate using finite distances. To implement the above conversion, what would be the associated field? It is very easy. So this is my y direction. This is my x direction. So I have to subtract x plus 1 y. So at that location, so okay, this is that location. I am double lining that. This is my x naught y naught. So this is x plus 1. This must be 1. That 1. And here it must be negative 1. This negative 1. That's the kernel. That's the kernel. It's very simple. If you run this kernel, you will get the derivative. But the thing about this kernel is this is not symmetric. These are symmetric. So therefore we don't like that too much. So what we want is we have to slightly change the kernel and write a 0 there. 0 there and put 1 here and put minus 1 there. So this is the central difference formula. We call it central difference formula in finding the derivative. This is the forward difference. Forward difference. This is central difference. Central difference is what you should apply. Okay. Here is an example question for you. So, yeah, partial derivatives of an image. So, question for you. So, x direction is this one, y direction is that one. What image is, okay, we have two derivatives A and B. I'm asking you, what is a partial derivative of the image? Let's call this image F. F x. What is that? So can you please type the answer? I'm asking which one is partial f by partial x, A or B? Which one is partial derivative of f by x, A or B? Means vertically downward direction. Please try to answer, all of you. So partial derivative of f with respect to x means vertically downwards. So we will be running a kernel like that, right? We'll be running a kernel 1, 0, minus 1. That's the kernel we'll be running. So which image is that? So if you run a kernel like this, what should it detect? It should detect bright, dark, dark to bright transition, dark to bright transition in the image. If there's a dark to bright transition, it must emphasize. Okay, what are the places where dark to bright transition vertically downward is there? Vertically downward dark to bright transition is there here. That must be emphasized. That kind of transition is sort of here. Those must be emphasized. So those are emphasized in this image. This is emphasizing the horizontal edges. This is emphasizing the vertical edges. Yeah. Okay. I hope that is clear to you. So this one is a partial derivative with respect to y. This is with respect to x. Huh? The answer is B. Okay. So to run this, you can run a kernel like that. To run this, you can run this kernel. But you know that we don't like this kernel, this forward difference formula or the backward difference formula. We like the central difference formula. So even to improve these central difference formulas, we have the Sobel kernels and the Prewitt kernels. In the Sobel kernel, not only do we have the sort of central difference formula, but we have emphasized the central column. This is the central difference formula in this column. In this column, but we have emphasized the center. And we have added the neighbors a little bit. So because we don't want it to totally get affected by too much noise. That's why we have done that. So you have to remember the Sobel kernel format. I think we have seen it again and again. And Prewitt kernel, you know, Sobel, Prewitt, you know. Okay. All right. So we have already done that last time, applying the Sobel and the Sobel kernels. All right. So now let's look at what do these things look like. So at every single point on the image, you have two gradients with respect to x and with respect to y, as I have shown here. So therefore, at every location, since we have two numbers, it's a vector. At each location, you have vector. It's a vector field. It's a vector field. Why do we call it a vector field? Because at every location, you have a vector. It's a vector field. So we denote this because it says it's a vector gradient of f. Then this operator is called nabla, right? Gradient of f, grad of f. So okay, let's look at this grad of f. So now if you take this edge, which one is a non-zero number, which is a zero number? Partial derivative of f with respect to x or partial derivative of f with respect to y, which is non-zero. So this is, remember, this is x direction and this is y direction. Okay, in this case, you can see there is no transition vertically downward. So therefore, partial derivative of f with respect to x must be zero. Partial derivative of f with respect to y must be non-zero. So you can see the first number is 0. Second number is there, it's non-zero. We take this one, the opposite, right? X is non-zero, y is 0. Okay. Then if you take this one, both are non-zero. Like some edge like that, right? Is kind of an edge like that, both are non-zero. So with this, you can, the gradient points in the direction of the most rapid increase in intensity. So most rapid increase in intensity is that way in this one. So gradient points in that direction. How does this direction relate to the edges? It is perpendicular to the edges. So gradient is this way, edge is this way, right? So gradient is perpendicular to the edges. So edge is this way, gradient is that way, so perpendicular to the edges. This is the area. Also, the gradient direction can be found by tan inverse. And then strength of the gradient, we can square the gradients and get the square root, because that is how you get the magnitude of a vector. So with this, you can do funny things, like you can extract these things and replace, and all these funny things can be done. So if you like, you can go to this this paper and see how that has been done. Okay. All right. So now let's look at how to filter the noisy images, effect of the noise. So now let's take a one-dimensional image. So remember, the one-dimensional image means you have the 2D image and this is noisy and you get a scan line, right? So that's the one-dimensional image. So you can see this image is a dark to bright transition image, right? Dark to bright transition image. You can see the noise is there. Okay, so if this is the image and you run d by dx on this image, you get all noise. You cannot even see the edge. What is the reason for this? Now you can see this noise is high frequencies, right? It is like cos x, sin x, sin omega x. sine omega x. This omega is the noise frequency, right? So let's consider one term in the noise. So if you get d by dx of this, since this is 1d, you can call it d by dx. D by dx sine omega x. What is the answer? You have omega cos omega x, right? I hope remember the derivative of sine omega x. Omega cos omega x. So you get the omega in the front. So if this is like 10 to the power of 6, 1 million, you get that multiplied by 1 million. Noise amplifies. So that's what you see here. Due to the derivative, noise amplification has happened. So what that means is before you detect edges, that is before you run the derivative operator, you have to smoothen the image. Otherwise, you will get whole lot of noise. So this is exactly what you need to do. First of all, you have F here. That's our image. That's our image. And then we have to run the Gaussian kernel to smoothen that. So this is, since it's a 1D image, I'm showing a 1D Gaussian kernel. So you run that and then your image gets smoothened out, noise is gone. But it, edge also gets blurred. This happens. So you can see by the convolution operator, we are showing the Gaussian smoothing. And then after that, you run the d by dx operator, then you will get a peak at the edge. I hope that's clear to you. But one thing is, to find edges, look for peaks in the d by dx f convolved with g. But as you know, d by dx f convolved with g is equal to f convolved with d by dx of h. Why? Because this is associative. That means if you have 3 times 2 times 5 or something, okay, you can do this first and multiply by 3, or right, you can multiply by 5 after doing 3 by 2 first. 3 times 2 first, right? Does not matter, for the same thing. So the convolution is also like that. You can associate. So therefore, first of all, you can run the derivative operator on the Gaussian. This is the Gaussian. G is the Gaussian. Derivative operator on the Gaussian and then convolve with the image. Okay, let's look at the Gaussian and see the derivative, how that should look like. I'm drawing the 1D Gaussian. Okay, I'm drawing 1D Gaussian. Is 0. At the 0, you have the P maximum. This is how the 1D Gaussian looks like. Okay. So now we have to plot the gradient of that. What does the gradient look like? Gradient. So here, gradient is 0. I hope you agree. Now the gradient will start increasing because you can see it's positive slope. Positive slope, highest positive slope will be somewhere here. Positive slope, 0 slope. So here it's 0. Highest positive slope will be somewhere here. And you can see it is goes like that and comes to 0. And then 0, negative slope highest, negative slope small and nothing. 0 here. So highest negative slope will be somewhere here. So you can see it goes like that. So you see, you can agree that this is the derivative of the Gaussian. D by dx g. That's the derivative of the Gaussian function. And you can run that on the image. If you run that on this fx, you will get a peak at the edge. This is the way to detect edges. So you have filters called derivative of Gaussian filters. Derivative of Gaussian filters. That how you do that? You take the Gaussian kernel. Today we understood how to conduct the Gaussian kernel, and you run the derivative operator on that, the central difference formula on that. That's all. That's all. Then you get get filters like that. You can see, right? This is not the Gaussian, derivative of the Gaussian. Can you see that how nice it is like that? Hump here, positive hump and the negative hump are located close by. Any questions about this image? Is that clear? Okay. So
Sir,
when you run,
is there
yes,
any reason where that flat part is green and then the top is red and the bottom is
this is yeah, that's because we have applied the color map called jet color map. That's the reason. We can do that actually.
a reason for applying that color map?
Yeah, just for us to see. There's nothing else. Just for us to see. Just for the purpose of seeing. So okay.
Okay, visualize.
Yeah. So this is the Gaussian kernel. So let me construct the derivative of the Gaussian field and show you. So this is the Gaussian. So let's have a sigma extend. That's okay. What we need to do is on this one, we need to run dx kernel. Dx is np.array. Np.array, that's one. We can write a d type also. So 32, that's fine. So that's the derivative. You can see minus 1, 1, 1, 1. And then g by dx is cv dot filter 2d g minus 1 dx. I hope it will work. And then this is what we want to draw. Can you see that? This is exactly what we had. So just run this filter on that. That's it. And you get that. So you got these colors because we have the jet color map. If you can use another color map. So what are the other color maps available? Something like that. Different color maps are there. Okay, that color map is jet. Let's see the color map I can get. That jet is all the color map it's going to give. Import color maps. Now I can get a color map there. Yeah, this one. If you apply a different color map, you can see different colors, right? So I mean, they don't mean anything. They just show you that which is high and which is low.
Yes, sir.
Yeah. So so you can see all the things that we do here in the slides can be implemented. They can be implemented with a couple of lines of code. So that's why I encourage you to go home and try to implement them. It's very simple, but you feel so happy when you do that. So okay, I have not answered that. Are these filters separable? They are also separable. You can write them like that. So Gaussian can be expressed as two product of two functions. One function x and another y. In this case, two functions are identical, one d Gaussian. So I think you can separate the derivative Gaussian also. I didn't think about it too much. Okay. So one thing about the scale of the Gaussian derivative filter. So if you just have one pixel sigma, then you get very small edges you detect. 3 pixels, coarse. 7 pixels, coarser pixels you detect of the giraffe image. Smooth derivative removes noise but blurs edges. Also finds edges at different scales. Okay. So if you briefly talk about these filters, smoothing filters, Gaussian removes high frequency component. It's a low pass filter. We understand that. Can the values of the smoothing filter be negative? Answer is no. What should the value sum to? Answer is 1. Remember, we divided by the sum of the Gaussian to make it 1. Otherwise, if you apply this filter to a white wall, the intensity of that will increase. That is the reason. Derivative filters of Gaussian, so things like that. And can the value of the derivative filter be negative? Of course, some parts are negative. What should the values sum to? They must sum to 0 because no response to constant regions. So these differences are there. And that's a summary up to now. So let's take a 15-minute break and then meet at 8:10. So until then, I will pause the recording. Of course, if you have a question, you can ask. I will also have a cup of tea or something and come. Thank you very much for waiting until this. Any questions? All right, then I'll pause the recording and come back at 8:10. Okay. I started recording again. So thank you very much for staying in class. So we looked at the derivatives. Now we will look at the so-called canny edge detector. This is a very famous paper and it's very useful to detect edges. It appears in IEEE transaction pattern analysis and machine intelligence. Still, this is the topmost journal in all of computer science, all of engineering. Filter. So this one filters an image with the Gaussian derivative of Gaussian filter. Now you understand what that means. Find the magnitude and orientation of the gradient. I hope you understand that. And then non-maximal suppression. I will explain that to thin the white ridges, and then linking and thresholding hysteresis. So that we will look at later. Okay, so now let's take this original image, a very bad image. And then what you do is you first of all get the norm of the gradients, that the gradient magnitude. So you can see for the edges, you have high magnitude, right? Norm of the gradient magnitude. Then after that, you do a thresholding so that small gradients are gone. You can see small gradients are gone. Thresholding. Then after the thresholding, you examine these edges. So you can see that these edges, they have a high gradient points. They have a width. So if you go this way, they have some width, right? It's not a one single pixel. They have some width. So if you take an image, a one-dimensional image, you can see the edge happens slowly, right? That's why when you have the gradient operator, so that has some width. So this whole area we call the edge. So what we want to do is to represent that using one single line pixel. That's why we need to do non-maximal suppression. So you can see we draw a perpendicular line to the edge. So computationally we can do that. And then we find the maximum point there. I will not go into more details than that. So with that operation, you can get single pixel lines. Now this is nice, but unfortunately, you can see some edges are broken. Problem is pixels along this edge didn't survive the thresholding. So what we want to do is, we want to have this effect of following the lead effect. Now, you know that those days, not anymore, those days, the honorable ministers, they have golas, right? Small supporters. Now assume that honorable minister is coming to going to a hospital or something, right? So it's the honorable minister. He just walks in. He just walks in. He's a powerful man. When the honorable minister is walking in, as you know, the Golabalas can also go behind him without a problem. But can the Golabalas go on their own to the hospital? No. They will not be allowed. Security man say, no, you go. You are a less powerful man. You cannot go. But if the honorable minister is going behind him, they can go. Like that, if there are powerful edges, those less powerful edges connected to the powerful edge will survive. Other less powerful edges will go. So this is called hysteresis thresholding. So you can see high threshold to start the edge curves and low threshold to continue them. So these are strong gradients. These are strong gradients. And those less strong gradients connected to a strong gradient will survive. Other less strong edges will diminish. That's what we had to do. So the original image is there. So these are all the strong edges, high thresholded, and these are the low threshold, weak edges also. And then these with the hysteresis thresholding, the weak edges are connected to the strong edges, so some weak edges also survive. Yes. Now I think you can understand how to do that. Compute the X5 gradients and find the magnitude and orientation of the gradient. Non-maximal suppression, thin white ridges down to single pixel. This is a little bit of a cumbersome computation. Linking and thresholding hysteresis. Define two thresholds, low and high. Use a high threshold to start edge curves and low threshold to continue them. This is how it's done. So I will code this and show quickly. Okay, this one we want to do the canny edge detector. Import CV as and matplotlib and so on. We can import CV2 as CV, and then I will open the image called there's a girl image. Girl image. I will open that image, and this girl image. I can open that using color. That's not a problem. It's not a problem. So assertive theme is not now. That is fine. Then I can apply the canny edge detector. Edges. Edges. Okay, so let me call this image. Now I don't need image. Image and edges. cv.canny. cv.canny. Oh, what happened? Very easy, right? cv.canny image 100, 200. So low threshold is 550, high threshold is 150, something like that. And then we display that. I will display that using OpenCV. So yeah, image and edges. Yeah, that's a way to display that. So I will run this and show you. You can see this is the girl image, and you can see the edges, right? Edges. So these are the canny edges. They are single pixel thin edges. But I did not demonstrate you the hysteresis thing. For that, I have a code written. So I will copy that code rather than trying to write it in front of you. So there, I have mouse callback function. I can click, I can draw the tracker bar is there. So I can control the low threshold and high threshold. So you will see. Okay, don't look at it right now. Okay, so now you can see if I control the high threshold, you can see edges start disappearing, right? High threshold means I am very selective now, very selective. I retain only the very strong edges are now there in the image. Only very strong edges are there. You can see, right? With the high threshold controlling. Okay, now these edges, let's say these are the high threshold edges. But if I lower the low threshold, now you can see small edges start connecting to them. Can you see that? Start connecting to them. They continue like the Goliaths of the Honorable Minister. They are walking behind the high threshold edges. Can you see that? So high threshold controls the number of edges, and low threshold controls the amount of edges that are connected to these high threshold edges. So I hope it is clear what the low threshold and high threshold mean in the canny edge detector. Any questions about that?
So what are the use cases of this kind of filtering?
Canny edge detector is very useful. Saying that you are running, you want to detect the shapes on a conveyor belt. Some components are going, you want to get the edge, right? You get the edge and you detect the shape of that object. So these kind of things, they are very useful. We'll do some practical ones when we cover some material.
Okay.
So
So second question is, when we do this filtering of images, does the size of the image increase, or does it stay the same?
By size, if you mean the height and the width of the image, it stays the same.
So when we save it, it will be the same size.
When you say you are talking about the file size,
Yes, sir.
then file size depends on the operation that you did and the compression algorithm that you use. So if you blur using a Gaussian, and if you save as JPG, file size will reduce because not much information is there.
Okay, sir.
Yeah. Okay, so that's a good question. Okay, so now it's the canny edge detector. I think you understand what that means. So you can see the people have developed so many edge detection algorithms, and this is the gradient magnitude, and human segmentations are there, and then This is the ground truth, the output is now getting closer and closer to the humans. Okay. Now let's look at how to detect corners. Edges now we know. Now let's understand how to detect corners. So these are the corners, as you can see here in this image. Corners have been identified using these little things, as you can see corners, right? Yeah. Okay, so these corners have extremely important usages like panorama stitching and so on. Like, for example, if you have two images like this of the same scene, we can extract these so-called features. And these ones, the same features, for example, this one, can be redetected in the, maybe that's not there. This one, for example, it's there in the other image also. So match them, we match them. You can see same features, you match them. So to match them, you have to assign some kind of a signature. So we will understand how to assign that kind of a signature. And then we can align those images. This is called panorama stitching. You can see the second image has been aligned to the first image. So one thing that must be there is the repeatability. In these features that we did, the same feature can be found in several images despite geometric and photometric transformations. That's repeatability. Saliency, each feature must be distinctive. That means this must not look like this one. There have to be difference in the representation. Compact and efficiency, many few features than image pixels. So image pixels are maybe 1000 by 1000, but you don't have that many features. Locality, a feature occupies a relatively small area in the image, robust to clutter and occlusion. So these are the characteristics of good features. So there are applications. Feature points are used for image alignment, as we saw in the previous example. 3D reconstruction, obtaining a 3D reconstruction of the image. We will look at that later in the lessons. Motion tracking, robot navigation, indexing and database retrieval, object recognition. For all these things, those days these features were used. So these features were handcrafted those days, but now you know that they are computed using the convolutional neural networks. So here is an example of the Mars rover's weave. So here you can see its weave over there, but you can see in the other image, it is right here. So no human being can identify that, but using features, we can identify what the rover is looking at in this large image. Okay. So corner detection, basic idea, let's look at that. We should easily recognize a point by looking through a small window. So you can see the convolution operator, they have small kernels like 3 by 3, 5 by 5. By looking at those, we should be able to identify that's a corner. Shifting on a window in any direction should not give a large change in the intensity. So I will show you with examples that. So for example, now take this. This is a flat region in the image. So this black region, you can see this black region. This black region. Okay, you can see that the corner is here, right? This black region. Now we have located our window right here. If you move the window little in this direction, or that direction, or that direction, nothing changes. Flat region, no change in all directions. But if you take an edge, if you move in the vertical direction, no change. But if you move in the horizontal direction, there is change. No change along the direction, but there is change perpendicular to the edge. But if you look at the window at a corner, any small motion will change what is seen inside the window. So significant change in all directions. That's the way to detect a corner. So now this is the intuitive way of looking at it, but now we have to mathematically characterize that so that we can implement that on a computer in an algorithm. Okay, so let's look at that algorithm. It is slightly mathematical, but I think you are able to understand that. All right. So let's take this one, change in appearance of window W with a small shift. That's what we are looking at. So this small shift of U and V. So you can see we have the image, I is the image, and IX and IY is a particular location in the image. And we have added a small shift to that image. Small shift. Okay. So you can see this IXY. Okay. So then we have located this W window there. And then we are slightly moving that window to this location. Okay. So that the window center has been moved to, yeah. let's say this location, the window center has been moved to the right? Center of that window is here. Window center has been moved here, right? When you move that window, is there a difference between the red window and the green window? That's what we are checking. So this is the green window. This green window. This is the red one. That's the red one. Is there a difference if you slightly move? So that's what this function will tell you. We are subtracting, and we are, for each of the u values and each of the v values, we are plotting this difference. So if there's no motion, that means when uv is 0 and 0, this is 0, this is 0, u and v are 0, 0, of course it is black, there's no motion, there's no change. If you slightly move it, there is some change, slightly move it, some change, slightly move it, some change, slightly move it, some change. If you move by a large amount, that means these are far away motions, right? Then quite a bit of change. That's what this EUV error function shows you. I hope you understand that. If you have a question, you can ask me. Okay. All right. So this is E00 and so on. All right. Now we want to mathematically explain that. We want to find out how this function behaves for small shifts. So first order Taylor approximation is what we are using. I hope you remember the Taylor approximation. It is not difficult. If you remember now, if you have a function f and the value of that function at x is a constant plus h, right? We find using the Taylor approximation, right? So that is equal to approximately equal to the fx itself, fx plus, do you remember how the next term comes? H times the first derivative of fx at x plus h squared over 2 times f double prime x. I hope you remember this. If you don't, I mean, no big deal. And other higher order terms. That's a Taylor approximation. So in this image processing thing, we only take the first order approximation. Only these two terms we consider. Only these two terms we consider. We don't consider these terms. So, but it is 2D, right? So you have u and v. So this is h in x direction. This is the h in y direction. So therefore, when you write ixy, you have to write ix partial derivative in x direction, iy partial derivative in y direction, and multiply the respective variable. So you can see this is the Taylor first order Taylor approximation of this image's value at x plus u and y plus v in terms of its value at x plus y. These are the gradients. So that you can see why we studied gradients that much, right? Gradient is required everywhere. Okay, so now this is very easy. You take that and plug that in here. Plug that in. What happens? This xy will cancel off. Right? This xy, this ixy, this ixy will cancel off because there's a minus sign. And what you have is this one. Ixu, iyv squared. If you square it, you know you get this squared, second term squared, twice the first term and the second term multiplication is what you get. And you can write that as a matrix form. You can write that as a matrix form. You can write it as uv. Of course, we know that we love matrices. uv. And that's a 2 by 2 matrix. And then uv. Here you will have ix squared. Ix squared. Here ixy. Ixiy. Here also ixiy. Here iy squared. For example, if you take u squared, for example, so this will multiply with this one, that one will multiply with u, right? So you can see ix squared is the multiplier of u squared. So you can see this is the matrix representation of that. But remember, then there is this summation xy over w. So that I forgot to write here. I did not write here. So that summation will come. It is very important to have that summation. Summation over window. So you can see this matrix has a special name. It's called M, called second moment matrix. So that's my M, second moment matrix. You can see these are the things. I hope it is understandable to you. This is very valuable. Okay. So if you get the second this matrix, if you can now, this is like this is a very simple thing. It's like something like this, right? It's like 5 x here times x here, something like that, right? You have the matrix M at the middle, and you have UV. Of course, it's two-dimensional UV. It's like x times 5 times x kind of thing. So this is 5x squared. Right? In 1D, this is 5x squared. What is the graph of 5x squared? And you all know the graph of 5x squared is a parabola, like that. Right? This is 5x squared. So in 2D, it looks like a coconut shell, pole cutter. Like that. That's graph. So that will have a well-defined minimum, because this is a second order expression, quadratic expression in 2D. It has a well-defined minimum. So that is what you see here, that minimum. So this is your M. The surface EUV is locally approximated by a quadratic form. Let's try to understand its shape. Specifically, in which direction does it have the smallest and greatest change? So that depends on the shape of that, whether it's like a oruva or whether it's like a coconut shell itself. So whether it's like a boat or a coconut shell, like depends on M's values, it will change the shape. Right? So first consider the axis aligned case. Gradients are either horizontal or vertical. So that means these numbers are 0, this number and that one are 0, and this has a value and that has a value. It's axis aligned. Gradients are axis aligned. That means a corner like that. The corner is axis aligned, aligned with the x and y axis. If either B or A or B is close to 0, then it is not a corner. So look for locations where both are large. When both A and B are large, it's fine. It's a corner. Consider a horizontal slice of EUV. It's a constant. So these slices are as seen by either circles or ellipses. This is an equation of an ellipse. So we can diagonalize M. We can get M equals some rotation makes R inverse R, lambda 1 and lambda 2. Those ellipses sizes will be given by linear algebra, lambda max to the power of minus half, lambda min to the power of minus half. So this is the direction of the slowest change, this is the direction of the fastest change. The axis lengths of the ellipse are determined by the eigenvalues. These are called eigenvalues, and the orientation is determined by the R. So in the image, at different corners, you can locate these ellipses. You can see that. And you can specifically see at corners, at very corners, those ellipses are like circles. I hope you can see that. At edges, those ellipses are thin and long. Thin and long. At corners, they are circles. At edges, they are thin and long. This is the criteria we have to see. We have to see. So this ellipse's elongation, or whether it look like a canoe, or whether it looks like a coconut shell, is determined by those eigenvalues. So you can see if both the eigenvalues are large, that gives a circle, so that's a corner. If both eigenvalues are small, that's a flat region. If only one eigenvalue is large compared to the other, it's an egg. This is the corner detection criteria. You can see strong mathematics, but by observing the physical phenomena. So this is that one, classification of image points using eigenvalues of M. So this is the one eigenvalue, is the second eigenvalue. If lambda 1, lambda 2 are both small, is almost constant in all directions, it's a flat region. If one eigenvalue is large, it's an edge. One eigenvalue is large, the other, it's an edge. If both eigenvalues are sort of equal and large, it's a corner. This is the corner detection criteria. Both the eigenvalues must be large. equal and large. Now,
What's the reason for the picture like this shaped like a kite? Is there any reason for that, or
yeah,
it's
you
just
can see that now this is the lambda 1 axis, this is the lambda 2 axis, right? This is the lambda 1 axis and this is the lambda 2 axis. So in this axis, so in this region, both are small. Both lambda 1 value is small, lambda 2 value is small. That's a flat region. If you take some location like that, lambda 1 is this much, lambda 2 is this much, that both are sort of large. So that's why that is represented by.
okay.
Thank you for that question. So that's it. But computing these eigenvalues is usually expensive. You have to spend computational power for that. So therefore, there's a similar but less computationally expensive criteria called the Harris criteria. This was described by Harris and Stevens. It's called the Harris measure R, determinant of M, and the trace of M squared. So determinant, I think you know that if you have these are 2 by 2 matrix, if you have A, B, C, D, you know that determinant is found by AB minus CD, right? AB minus CD. That's a determinant. It's very easy to compute. Trace means A plus B. So very easy to compute this. You don't need to use singularity decomposition or something for that. So alpha times trace. So alpha's value is 0.04 that they have found by experimentation. This is the way to, this is the Harris measure. So when Harris measure is magnitude is small, it's a flat region. When it is less, it's an edge. Less than 0, it's an edge. When it is greater than 0, it's a corner. This is the Harris criterion. Yeah, you have to remember that. Okay, so what is the Harris corner detector thing? Compute the partial derivatives at each pixel. So this one you can write in 15 lines. Harris corner detector now in Python. 15 lines. So you know how to compute the partial derivatives. Run a Sobel operator. That's it. Run the Sobel operator in y direction and then you multiply them. Actually, you have to blur them using a Gaussian window and sum them. So that is your M. At each location, you have an M. Compute the second mode matrix in a Gaussian window around each pixel. Compute the corner response R by using this trace and determinant criteria, determinant minus alpha times trace square, and then you'll get this cornerness. So this is the cornerness response, R. You can see at corners, the R is very high, right? Red means high, blue means low. But then you have to do the threshold R, you threshold R and find the local maximum. You threshold R, but they are not corners, right? I mean, they are a set of corners. So we don't like them, so you have to find the local maximum there. When you find the local maximum, you get dots for corners. Sorry, get dots for corners. And if you plot those corners in the images, you can see in both the versions of the image, for example, this corner has been detected in the other changed image also. This corner has been detected in the change image also. So that's the Harris detector. So if you have time, please spend 1 hour to implement the Harris corner detector. It will be a very good exercise.
So can you just explain what's the difference between corner and edge and based on these images we're looking at?
Here you can see this is an edge. This is an edge, right?
It's like a boundary between two different.
Yeah, it's a straight line. It's a straight line, straight line, horizontal line, no vertical line, something like that. In a corner, there's, I mean, this is a corner, right? This is a corner, right? It's like a corner of a table.
Okay, edge of,
table.
okay.
Yeah. These are the physical meaning of it. If you take table, this is a corner. This is an edge, right? The same physical meaning is significant. Yeah. But corners are very important because corners can be relocated. Now think about an edge. Now you have a table like that. I ask you to touch this location. You touch it. Second day, can you come and touch the same location? You don't know where you touched. But if I ask you to touch this corner, the next day also you can come and touch the second corner. So the same corner. So corners, because they have 2 degrees of freedom, you can relocate them. That's the value of the corner. That's why we are very interested in corners. Because, for example, if you take this this horn of this cow, you can find the you can find the corner without detecting. I can say, okay, this is a corner in this image, The same corner is here in this image. I can do it, right? But if I draw a point on an edge, in the next one, I don't know where it is. That's the thing about the edge. Corners are very valuable because they have 2 degrees of freedom and we can relocate them. Okay.
Okay, thank you, sir.
Yes. So that's about the corner detection. So Harris corner detection is quite easy. I have the implementation also of the Harris corner detector. I will just show it. I will not run it, but I will show my implementation. Here is the implementation. You can see it's a very simple implementation. I hope you can see that. It's a very simple implementation. You can see I have computed the x direction gradient, the y direction gradient. This you already know. You write the Sobel kernel, right? And then I have M11, I have Gaussian blurred Ix squared. M22 I have gotten Iy squared. M12 and M21 are equal, Ix Iy. Very easy. Now I have the second moment matrix. Then I get the determinant, then I get the trace, and I get the Harris measure. That's it. That's it. Then after I have the Harris measure, of course I have to do this non-maximal suppression. This is annoying. This is annoying. So for that I use some function available in sklearn to do the non-maximal suppression. Then this is the original image. This is Ix, x directional gradient. This is Iy, horizontal gradient. And this is the R measure. For corners, you can see high response.
Sir,
And
what do you mean by that high maximum resolution? Something you said we had to. That's annoying.
the
What's that?
non-maximal suppression.
Yeah.
Non-maximal suppression is that's an important question. So now this is I'm saying this is a corner. No, where is the corner? It must be at the very center, right? Where the function is the highest. So brightest point is the highest. So I have to only keep the brightest point and remove all others. That's what called non-maximal suppression. Those who are not the maximum, you suppress.
Okay.
Then only I can get a single dot at the corner. Otherwise, I will get so many corners near that. So you can see I have got the corner there. This is actually very easy to implement. So okay, I have large image, so you can see to get one dot there, I have to do get rid of all the nearby points. So many nearby points are there. So many. I cannot enlarge that. Enlarge that it. Yeah. I cannot enlarge it. I think you understand, right? Non-maximum suppression. So for that, I'm using someone else's function. I don't know how to implement the non-maximum suppression. Meanwhile, it's possible, maybe. I don't know. So, okay. That's the Harris phone implementation. So you can implement that, but it will take a little bit of time. But if you do it, you will be very happy. Harris phone implementation. So next time we will see how these Harris corners whether they change with the image rotation, image translation, intensity changes when they rotate, or they change. After that, we will understand mechanism of making them invariant or covariant with these transformations. And then finally, we will look at the so-called very famous paper called, we will look at this so-called blob detection. And from that, we will understand how these so-called shift features are detected. Shift features are detected. There's a very famous paper that came in 2004. This one, no, not this one. Shift features. And shift features is this paper. Shift features are used in robot navigation and so on. And but now there are better features than shift features. If you look at the so-called call map or superglue. Coleman. These features are, you can see that they have been able to match across large cities, feature matching and detection. So that's the column map thing. Then super glue. They given the pre-trained network, so they call it super glue because they can match features across images very well. You can see those image matching has happened. These things are very fast. These super glue things, see? Extremely fast. So when you navigate a robot and so on, robots camera images change, right? So between frames, we want to match features. After matching features, only we would be able to understand, get a 3D understanding of the scene. So these things are very important. So if you get the CVPR, that's the best conference in the world. So VGGT was the best paper award. That also does, not exactly, much more advanced, some thing similar to that. They have a demo also. That they can reconstruct. Waiting for a GPU to become available. They don't have GPU, so they have to compute. They need a GPU, I think, free GPU. But until then, we can look at VGT. Fast enough for compute. No GPU, so they cannot run that. Some GPUs are required. Anyway, so you understand what that means, right? 3D. Okay. So some see, now you can obtain the 3D reconstruction. We have 30 reviews. Now you have the 3D reconstruction of that. So these happen with the feature measures and so on. But these features are actually OpenAI. Oh, sorry, not OpenAI. The deep learning based features. Right. They got the
So
best
is
paper.
this model like a photo geometry one?
Say it again. What like a?
Is it like a photo geometry?
It is from photos. Photo geometry means?
Like we 3D scan from photos?
Yeah, like that. Yes. 3D scan from photos is like you can do single photo 3D reconstruction things are there, but those things are not geometrically correct. These are geometrically correct. Using that, you cannot navigate a robot, no? In this case, with these ones, you can navigate a robot with this because these are correct. So that's the value of these things. Yeah, not only is the 3D reconstruction available from 64 weaves, but this mathematically correct. They are not just based on the weights of a neural network. So these are the final things that they have done with owners and so on. Thank you for that question. Okay, so I think we have understood this briefly and spent some time in understanding corner detection. So we will next time we will move with this and give you small assignments also to do, but it's not to burden you, but to make you do these things and be confident with these things. Okay, if you have any questions, you can ask. Otherwise, we are done for now. I will stop the recording.